In section 5.8, we look at systems of nonlinear equations. A system of nonlinear equations is a system involving two equations where at least one of the two equations is nonlinear. So in the example down below here, you can see that the second equation is a linear equation because the powers of x and y are both the first power. However, the first equation is nonlinear because one or more of the variables is raised to a higher degree power. Now what this basically means is that this equation here, when you graph it, is not a straight line. This one is a straight line, but a line and a curve can intersect in more than just one point. So as opposed to systems of linear equations where you can only get one solution, in the case where the lines intersect, for nonlinear systems, you can get several solutions. In our first example, we're going to use the substitution strategy. So here is the strategy listed here. Basically, what we're going to do is solve for one of the variables in one of the equations. We're going to substitute the expression for that variable in the other equation, and then solve the resulting equation for that variable, and then also plug that value in to solve for the other variable. So let's go ahead and take a look at this first example. So to solve this by substitution, I'm going to take the second equation, and I'm going to solve it for x. And I'll do that by simply adding 2y to both sides and subtracting 1 from both sides. And this will give us x is equal to 2y minus 1. And now we'll take the second equation, and since x is equal to 2y minus 1, we will substitute that into the second equation, replacing x. So when we do that, we get the following. Now that we've substituted x with 2y minus 1, all we have to do now is solve this resulting equation, which only has one variable. So we'll go ahead and multiply this out. And this is the result of doing that. So double check my work here. When you multiply this out, you should get this. Next, we'll combine like terms. 4y squared plus 4y squared is 8y squared. And then finally, we'll set this equal to 0 by subtracting 25 from both sides. And that gives us 8y squared minus 4y minus 24 is equal to 0. Now to solve this, I will use factoring. I can pull out a common factor of 4, which leaves us with 2y squared minus y minus 6 is equal to 0. And then I can continue factoring here. And I won't show the work for this factoring since it is relatively straightforward at this point in the course, but this is what we get for those two factors. And then finally, we set each one of those factors equal to 0 to solve for y. Here we get y equals negative 3 over 2, and here we get y equals 2. Now what we do is we take these two solutions for y, and we substitute them in here to solve for the corresponding values for x. So when y is equal to negative 3 halves, if we plug that in, we get x is equal to 2 times negative 3 halves minus 1. This is equal to negative 4. And for the other solution, y is equal to positive 2. And so x will be 2 times positive 2 minus 1, which is equal to 3. Now our solutions are points because we were finding points of intersection between these two curves. So the first point is x equals negative 4, y equals negative 3 halves. And the second point of intersection is x equals 3, y equals 2. And for visual confirmation, here is that first system that we just solved. I went ahead and graphed this on a graphing calculator. The green graph here represents x squared plus y squared equals 25. And the blue graph here represents the line x minus 2y plus 1 equals 0. And you'll notice that these two graphs intersect at this point here, which has coordinates 3, 2, and also this point here, which has coordinates -4, -1.5. And just for clarity, this is the same as -4, -3 divided by 2. So we can see that the line intersects what we call here is an ellipse in two places. So there are two solutions to this system. In the next example, we talk about the elimination strategy for solving a nonlinear system. So the strategy here is the same as the elimination strategy we talked about before. Basically, we want to eliminate one variable from both equations by combining the equations together. So we're going to add the two equations together, and then we solve the result and then substitute back in to get the other solutions. So let's go ahead and take a look at this example. So here, if I want to eliminate, the first thing I need to do is get our variables on one side and our number on the other side. So the first equation is x squared plus y squared equals 4. In the second equation, we don't want this negative 2x squared to be on the right side, so we're going to add 2x squared to both sides, and that will leave us with positive 2x squared plus y is equal to 2. Now from there, if I want to eliminate a variable, notice that we cannot eliminate the y because this is a y squared and this is just a y. But we can eliminate the x's because both of these are x squared. In other words, they are like terms. But to eliminate these by adding these two equations together, I need to have negative 2x squared here. So I'm going to multiply both sides of this first equation by negative 2. And when we do that, we get this system. And now you can see if we add these together, these terms cancel out, and we end up getting negative 2y squared plus y is equal to negative 6. And to solve this for y, I'm going to set it equal to 0, and I'm actually going to move the y terms to the right side of the equation. And the reason I do that is because I want my y squared to be positive. So I will add 2y squared to the right side, and I will subtract y from the right side. And now we just simply factor the resulting quadratic here. So we have 2y and y. We're going to have a 2 here and a 3 here, a minus and a plus. You can double check my work here. And then we set these equal to 0. And here we get y equals negative 3 over 2. And here we get y equals 2. Now we have to solve these for x by taking these solutions and plugging them into one of the first two equations. And I'll just plug them into the second equation. So let's start with y equals 2. If y is equal to 2 and we plug that in here, we get 2x squared plus 2 is equal to 2. Subtracting 2 from both sides gives us 2x squared equals 0. Dividing by 2 gives us x squared equals 0. And clearly, if we take the square root of both sides, we still have x equals 0. So the solution here is x equals 0, y equals 2. And if y is equal to negative 3 halves, we plug that into the same equation. We get 2x squared minus 3 halves is equal to 2. I'm going to multiply both sides of this equation by 2 to get rid of the fraction. That will give us 4x squared minus 3 is equal to 4. Adding 3 to both sides gives us 4x squared equals 7. Dividing by 4, we get x squared equals 7/4. And finally, taking the square root of both sides, we get x is equal to plus or minus the square root of 7 divided by the square root of 4, which is 2. So here we get two solutions. We get x is equal to positive square root of 7 over 2 when y is negative 3 halves. And we get x is negative square root of 7 over 2 when y is negative 3 halves. So we have a grand total of 3 solutions. Let's take a look at a graph. So once again, here is the system that we just solved. The first graph, x squared plus y squared equals 4, is a circle of radius 2. And the second graph, y equals negative 2x squared plus 2, is a parabola that opens downward. And you can verify from the picture here that we have three solutions. We have a point of intersection here, which occurs at 0, 2. And we have 2 points of intersection down here, which occur at these points. And just for reference, these were the solutions that we got algebraically on the previous page. And just for reference again, the square root of 7 divided by 2 is approximately 1.323. So you can see radical 7 over 2, negative 3 halves, is this point. And negative radical 7 over 2, negative 3 halves, is this point. For some systems, if you try to solve it algebraically, you will run into some difficulties that we are not prepared to deal with at this point. We need some methods that we learn in calculus to be able to solve some of these systems. So for this following system, xy equals 1 and y equals negative x squared plus 3, if you attempt to solve it algebraically, you can take xy equals 1 and solve for y by dividing by x. And then you can take y equals 1 over x and you can substitute it into here. And if you do that, you get 1 over x equals negative x squared plus 3. And then what you would do is you would multiply both sides by x, like this. And that would give us 1 equals negative x cubed plus 3x. And then moving everything to the left side, you would end up getting this equation. And this is an equation that we don't yet know how to solve because there are no rational solutions to this equation. So something like synthetic division, for example, fails to yield a solution here for us. So we don't really know how to continue here. So in these instances, what we can do is we can just use a graphing calculator. So that's what we have here. We have x times y equals 1. That is this graph here. It's also this graph here. And then y equals negative x squared plus 3 is a parabola that opens downward. And you can see that there are 3 points of intersection, and they are highlighted here, here, and here. And along with that, you can see approximate solutions for each of those points. So graphing utilities can be extraordinarily beneficial when solving a system of equations that is difficult to solve algebraically. However, we still want to maintain our knowledge of solving algebraically because that is truly the mathematics behind what we are doing. But it is nice to lean on technology for some problems. For our last example, we are given an application from geometry. It says a right triangle with a hypotenuse of 2 radical 15 inches, right here, has an area of 15 square inches. Find the lengths of the other 2 sides of the triangle. Okay, so what do we know about x and y? Well, one thing we know is the Pythagorean theorem is always true for a right triangle. And the Pythagorean theorem says if you take this leg and you square it, plus you take this leg and you square it, you get the hypotenuse squared. Now, what else do we know about this triangle? We know that its area is 15 square inches. Well, the area of a triangle is 1/2 times the base times the height. And the base of this triangle is x, and the height of this triangle is y. Right? So here's the base, and here's the height. And we know that that's the height because this is a 90-degree angle. So the other equation that we get is the area, which is 15, is equal to 1/2 times x times y. Now what I can do with the second equation is multiply both sides by 2. That will cancel the 1/2 that we have here. And that gives us x times y equals 30. And then the first equation is x squared plus y squared is equal to 2 radical 15 squared. Let's talk about that. 2 radical 15 squared is 2 squared times radical 15 squared, which is 4 times 15, which is 60. Now we can solve this system using the methods that we've discussed previously. Me personally, I like the substitution method a little bit better for this. So I can take this first equation, divide both sides by x to get y equals 30 divided by x. And then I can take that and I can plug it into here. Plugging that in gives us x squared plus 30 over x quantity squared equals 60. This is x squared plus 900 over x squared is equal to 60. Just a quick note here, what I'm doing is I'm squaring the 30 here and squaring the x. And then the next thing I'm going to do is multiply both sides by x squared to get rid of the fraction. X squared times x squared is x to the 4th, plus when we multiply x squared times 900 over x squared, we simply get 900. And on the right-hand side, 60x squared. This is a polynomial equation, so I will subtract 60x squared from both sides to set this equal to 0. And from here, I can try factoring. So to get x to the 4th, we have x squared times x squared. And to get 900, we'll have to think about what factors of 900 will work. For this one, it's pretty straightforward because we know that 900 is 30 times 30, and we know that 30 plus 30 is 60. So we're going to have 30 here, and both of those will be negative. And then we set each of these factors equal to 0, but notice that the factors are the same, so we don't have to do double the work here. We end up getting x squared equals 30. And after taking the square root of both sides, we get x is equal to plus or minus the square root of 30. However, this means that x is only equal to the square root of 30 because remember, x is the base of this triangle, and the base of a triangle cannot be a negative value. So we know that x is equal to 30, and if x is equal to 30, we can solve for y up here. We know that y is 30 divided by the square root of 30. And if we multiply by the square root of 30, top and bottom, we get 30 square root of 30 divided by 30, which is also the square root of 30. Now, if you go back to the beginning, it says find the lengths of the other two sides of the triangle. So we have it. X equals the square root of 30, and y is also equal to the square root of 30.